Our dynamic universe. The key areas covered will be the Doppler effect observed in sound and light, and the Doppler effect causing shifts in wavelength of sound and light. What we will do today is state what is meant by the Doppler effect, describe how the Doppler effect affects sound and carry out an experimental demonstration to show this, and carry out calculations on the above. The Doppler effect. So what is the Doppler effect? It is the change in frequency you notice when a source of sound waves is moving relative to you. When the source moves towards you, more waves reach you per second and the frequency is increased. If the source is moving away from you, fewer waves reach you per second and the frequency is decreased.
The Doppler effect. In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch, and then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
Moving source. As you can see, as you move closer to a source, the frequency you receive increases. As you move away from a source, the frequency you receive decreases. Calculating the frequency. When a source produces a sound of frequency Fs, we can calculate the observed frequency, Fo, using a formula. The formula changes slightly depending on whether you move towards the source or move away from the source. Calculating the frequency moving towards the source. The observed frequency, Fo, is higher. Fo equals Fs multiplied by V over V minus Vs, where Fs is the frequency of the source, V is the speed of sound, which is approximately 340 meters per second, and Vs is the speed of the source. A way to remember this equation is that towards is take away. Within your equation, it's V take away Vs, and this is when you move towards the source. Towards is take away. Calculating the frequency moving away from the source. The observed frequency, Fo, is lower. Fo equals Fs multiplied by V over V plus Vs, where Fs again is the frequency of the source, V is the speed of sound, and Vs is the speed of the source. A way to remember this one is away is add. So you've got your two A's there. Away is add. During this equation, it's V plus Vs. Away is add. What is the frequency heard by a person driving at 15 meters per second toward a blowing factory whistle with a frequency of 800 Hz if the speed of sound in air is 340 meters per second? First, let's write down what we know and what we don't know. So our F0, the frequency that the observer hears, is what we want to work out. Our frequency of the source is 800 Hz. Our speed of sound is 340 meters per second. And our speed of the source is 15 meters per second. We want to figure out what equation we want to use. So it's always going to be F0 equals Fs and V over. Are we going to use take away or add? Well, we're going towards the factory whistle, so we use take away. So V take Vs. Let's add in our numbers. We've got 800 times 340 over 340 minus 15. Popping that all into a calculator gives us 837 Hz. What frequency would the person hear after passing the factory if they continue at the same speed? Again, let's write down what we know and what we don't know. Again, it's our observed frequency we don't know. The frequency of the source is 800 Hz. Our speed of sound is 340 meters per second. And our speed of the source is 15 meters per second. This time the equation we want to use is F0 equals Fs V over V plus Vs. As we're going away, we want to add because we're moving away from the source. So adding in these numbers, we've got 800, 340, 340 plus 15. And popping that through a calculator, we get 766 Hz. A train is travelling at a constant speed of 16 meters per second as it approaches a bridge. A horn on the train emits sound of frequency 277 Hz. The sound is heard by a person standing on the bridge. The speed of sound in air is 340 meters per second. What is the frequency of the sound heard by the person on the bridge? Again, let's write down what we know and what we want to find out. We want our observed frequency, because that's the frequency is heard by the person on the bridge. The frequency of the source, we're told, is 277 Hz. The speed of sound, we've got 340 meters per second. And the speed of the source is 16 meters per second. Now the equation we want to use is going to be the one with a takeaway in it, as the train is moving towards the person. We can see in the little diagram there, it even shows the person facing towards the train. The train is moving towards them. It's approaching the bridge. So F0 equals Fs V over V take Vs. Adding in our numbers there, we've got 277 multiplied by 340 over 340 take 16. And we get a final answer of 291 Hz. That corresponds to answer C.